Hello, my name is Tracy. I'm the hardware lead for Team Montana. I'm going to talk about the hardware and fabrication of our robot. Our robot is an autonomous line-following robot that has front-wheel drive and is powered by two DC motors, which are attached to a 3D printed chassis that Team Montana designed in CAD. The design of the chassis was intended to minimize weight while still maintaining enough support for the rest of the components to sit on top. The robot is controlled by an Arduino with a mini breadboard expansion pack that provides extra input and output ports, such as more ground ports and extra 5-volt ports than what comes available on the regular Arduino Uno. We needed these extra ports because our robot uses two photoresistors to detect tape, and without these extra ports, there wouldn't have been enough room on the Arduino for the H-bridge, which powers the motors, as well as the photoresistors, and as well as the two LED lights that we have as our extra feature. A blue LED light turns on when the right photoresistor senses tape, and a white LED turns on when the left photoresistor detects tape. This feature was useful in the testing phase, since I discovered that the two photoresistors in my kit had slightly different sensitivities. Here's a table of all the circuits in the robot. I used some of the rows in the mini breadboard to connect a bunch of ground wires together, and some of the other rows were used to connect a bunch of wires that all needed 5 volts. For the LED lights, I just stuck the resistors directly into the breadboard, but for the photoresistors, the two 20 ohm resistors were wired using jumper cables, and this was because the placement of the photoresistors needed to be more flexible, so I didn't want too many components to be stuck into the breadboard.
Hello, I am Alex Haas, and I am the project engineering lead for Team Montana. I wanted to start by discussing some of the motivations of why we are doing this project. Our first motivation would be to become familiar with a large collaborative project that spans multiple weeks. Our second motivation would have to be to improve our understanding of things like circuitry, coding, and hardware assembly. Our third motivation would be to improve our knowledge of the engineering industry as a whole, such as what customer needs are and translating them into technical specifications. Our fourth motivation would be to become familiar with the engineering design process. And finally, to become familiar with the engineering roles in an engineering team. So yeah, those are our motivations.
Our final design for our robot, we used the design cycle throughout the semester. The first two steps were to identify the customer needs and engineering specifications. So customer needs were basically a line following robot, or any autonomous following robot for that matter. It had to be lightweight and inexpensive. For engineering specifications, it had to be 6 inches by 6 inches by 6 inches, and it had to have one novel feature to it. When brainstorming and creating concepts, we first brainstormed a box-light robot that had a line follower, and then a car-like robot that used photoresistors. When selecting the concept and testing, we used the car-like robot. However, we used the line follower on it, and it was able to make turns based on tape on the ground. We used a 3D printed cover on it that was attached to the chassis, and would have painted windows and headlights, because we were originally going to use the photoresistors for the headlights, but we thought that was impractical. So for our final robot and final specifications, we have a robot that is 5.48 inches by 3.396 inches. It has a 3D printed chassis and is a line following robot. It's able to make 360-degree turns and move forward and backwards. It has LED lights that shine when sensing tape on the ground, and it is also relatively inexpensive.
Hi, I'm Christopher Brent, the software lead at Team Montana. For the software of our robot, we wanted it to follow a line on the floor that was made out of tape. And because we had the hardware lead have sensors on either side of the robot, we could make it so that as one of the sensors detects the tape, the robot would turn in the direction of that side of the robot. So if the sensor on the right detects tape, then the robot would turn to the right. And that would mean that the robot would stay on top of the tape, and if the tape were to curve or if the robot wasn't moving straight, it would eventually hit the tape and then correct itself. So that's how the robot stays in line as it moves forward.
Hello, I am Kaylee Bransky, and I am the testing lead for Team Montana. Our robot had a net weight of 300 to 500 grams, a size of 5 inches by 4 inches. The maximum speed was 12,000 RPM, and the robot can be built within 6 minutes, assembled within 6 minutes, and the power is used by a 9-volt battery, which can be changed over time. And we also used a photocell to sense different colored tapes. Depending on the light or dark colored tape, it had to be within 1/4 to a 1/2 inch away to sense it. And the robot was able to turn 360 degrees. In conclusion, Team Montana did a fabulous job at collaborating with each other, and the robot turned out to be $23.93, so it was under $30, and it was able to fit in a 5x5 box, so it was under the requirement, and it was also able to interact with the children in a way that they can drive it and they can follow a line. Our team recommends that if a child is using the robot, that they are under adult supervision so that they don't have any choking hazard, because certain pieces can rip off and it would be terrible if a child were to swallow it and choke. And also, we recommend that the car is driven on a flat, smooth surface, so it is easily able to glide and have a maximum speed. Batteries should be new to ensure that the functionality is the best. And also, if you want to have the robot follow a certain line, that you use colors that stand out, which are like bright and vibrant, so that the sensor can pick it up.